While we are mostly looking at two-dimensional motion, we do need to be aware that there are three dimensions to reality, three spatial dimensions, and we need to be able to deal with vectors in three dimensions as well. In mechanics and physics part 1, we're going to mostly keep to 2 dimensions, but we get into three-dimensional vectors in physics part 2 specifically, and so we need to introduce that idea now. When you have three-dimensional axes, you have to use what's called a right-handed coordinate system by convention. What that means is that if you use your standard XY plane, where X is horizontal and Y is vertical, your third dimension, your Z dimension, is pointing out of the page at your face. The negative Z direction is pointing into the page away from you. When you see three dimensions in Calc 3, for example, you may also see this version here where the x-axis points out at you and the y-axis points to the right and the z-axis points up. This coordinate system is the same as this one. If we look on the z-axis and here is our eye looking down the z-axis, we would see the xy plane in front of us. It would be like us looking at this flat on the page. We've talked about unit vectors. The I hat unit vector points in the x direction. The j hat unit vector points in the y direction, and we have a new unit vector here. The k hat unit vector points in the z direction. So it behaves just like the k hat vector points in the z direction, just like the I hat and j hat vectors we have used before. So when we have these vectors, we can deal with them. When we have three-dimensional vectors, we can break them up into components, and we have 3 one-dimensional problems here, just like when we have two-dimensional vectors, we break them up into components, and we have 2 one-dimensional problems. One way that we can describe vectors in terms of magnitude and direction is borrowing from spherical coordinates. In spherical coordinates, we have a magnitude and we have 2 directions to measure, two angles to measure the direction. So this accounts for our vector. The vector has a magnitude and a length, and then the orientation of the vector is described by these 2 angles, phi and theta. And so phi and theta are defined thusly. The angle theta is a polar angle. You imagine the vector pointing straight up, pointing along the z-axis, and the theta angle measures how far that angle rotates from the z-axis down towards the xy plane. So theta in this case could be anywhere between 0 degrees and 180 degrees. If theta equals 0 degrees, that means there's a 0 degree angle between our vector and the z-axis, or our vector's pointing straight up. If theta is 180 degrees, that means there's 180 degrees between the z-axis and our vector, meaning it's pointing straight down. And if theta is 90 degrees, there's a 90 degree angle between the z-axis, which would mean our vector is in the xy plane. There's also a rotational angle. This rotational angle is phi, and phi rotates about the z-axis. So phi is rotating about the z-axis, and it could be anywhere between 0 degrees and 360 degrees. So phi is the same angle for rotation in the xy plane that we've seen before for two-dimensional vectors. So phi equals 0 is on the x-axis. Phi equals 90 would be on the y-axis. And as you keep rotating, you go around the z-axis in the xy plane, just like you've seen for vectors in 2 dimensions. The third dimension is described by theta, which is, again, our polar angle, also called the azimuthal angle. It's telling us how far we are above or below the xy plane, how far we are from that z-axis. So there are a couple relationships here. If we look at our vector in 3 dimensions would have x, y, and z components. We would start at the origin, and we go out in the x direction, and we go over in the y direction, and we go up in our z direction, and that would be our I hat, j hat, and k hat components for our vector in Cartesian form or in rectangular form. If we look at the vector in terms of the polar coordinates, in terms of using these angles to describe the direction, we can look at the magnitude of the overall vector. Here I have the overall vector in blue. And I can do a couple things. Number one, I can see that the x component of my vector in pink and the y component of my vector here in purple, these two together are creating a right triangle because x and y are perpendicular to one another. And the hypotenuse of that right triangle is what I call AXY. AXY is the component of this vector A, the component that is in the XY plane, because this is flat in the XY plane. And so the magnitude of AXY is the square root of the sum of the squares. This is Pythagorean theorem. We've seen that before. But if we want to find the magnitude of the overall vector A, this overall vector A is part of another right triangle. One side is AXY, and the other side is here in orange. That's the z component, the vertical component coming up from the xy plane. So what we have is AXY squared plus AZ squared would give us the magnitude squared. And if we want AXY squared, that means we're squaring the square root, which cancels both of those. And so we end up with AX squared plus AY squared plus AZ squared. Square rooted gives us the magnitude of the overall vector. So we can find the magnitude of the overall vector in terms of its x, y, and z components. The rotational angle phi can be found using the x and y components, because we said that this angle here is in the xy plane. And so we can find it just like we found it before. We can use the absolute value of AY and AX to find the reference angle. The reference angle is the angle relative to the x-axis, and then you can add or subtract 90 degrees or 180 degrees or whatever the case may be to find the standard angle. The standard angle starts from the positive x-axis and rotates counterclockwise, as we've seen before. If we look at the angle theta, we can see here, if we sort of look at this triangle here, we can see here that we have AZ is the vertical component right here, looking this way at it. AXY is coming across the top. And I should have changed my colors here. Here is my AZ coming vertically. And then this is my overall vector A. And theta is the vector that comes down from the z-axis, comes down here and rotates down to my vector A to there. And so we can see that to find the angle theta, we know we can find the cosine of theta if we know this component, and we can find the magnitude from this relationship. Then theta is going to be the inverse cosine of AZ adjacent over hypotenuse. If we know the three components, we can also find AXY. We find it with this equation right here. And the tangent of theta would be opposite over adjacent, and we could use the inverse tangent to find that theta, that other angle as well. We can also go the opposite direction. If we know the polar form of our vector, we could find the z component here. The z component is going to be the magnitude of the overall vector times the cosine of theta. That's that relationship here, because here AZ is our adjacent side. The full magnitude of the vector times the cosine of theta gives us that value. AXY is this side here. This is going to be A times sine of theta is going to give us the opposite side. A sine theta, you're seeing right here, A sine theta is projecting the full vector into the xy plane. And once you have the component of the vector in the xy plane, you multiply by cosine of phi, gives you the x component. Multiplying by sine of phi gives you the y component. And so you've seen using cosine of phi and sine of phi to find the x and y components of the vector. So when you have a vector in 3 dimensions, you can use the components to find a magnitude and to find 2 angles to describe the direction in 3 dimensions. Or if you have the magnitude and the angles, you can use those to find the components. That's important for us because whenever we are doing calculations, we want to break everything up into components, do all of our calculations, and then convert back to magnitude and direction.